So thanks, Ahmad, for inviting me. So I'm going to talk about distributed learning or distributed training from local parallelism to planetary computation. So I work at DeepMind. My topics is to work on distributed learning, but I aim to work on distributed learning methods that are a bit different from what usually people work, I would say. And in order to go beyond just distributed learning between like a small cluster of GPU to actually be able to use all the GPU across the world. So the goal of this session, I'm going to make a quick overview of existing methods that are methods that everyone currently use, even small labs. And I'm also going to talk more about what I believe should be the future of those distributed learning methods. I'm not going to go too much in the detail. It's more like to give an overview of what's existing and what I believe is the direction. That's my personal view. That's not the view of my employer, and that's probably not necessarily the view of the consensus of the community, both in AI and in distributed learning. I will also focus mostly on LLM. That's kind of the trendy thing. You know, everyone's talking about LLM. And I will focus on the pre-training side of the LLM, of course, the post-training. So I think you have a talk a few days before about how to do post-training or one-like and everything, thinking. The distributed aspect of the post-training is very different from the pre-training. So here I'm only focusing on the pre-training. I want to start first with the beta lesson. So I think, like in the previous lessons, you had like probably talks about like scaling laws, how to scale. So the beta lesson by Richard Sutton, which was written like 20 years ago, is basically that you can make a human-made innovation to make a model better. So for example, you can take like the convolutional neural networks, then the ResNet, then Adam, then the self-attention. All those algorithm improvements managed to make us better AI. But in the end, like the beta lesson is in the end, you can be as smart as possible as a human, but you want to develop a method that will be able to use as much as possible compute. And the amount of compute, so how many flops, how many operations per second we have been doing, has just climbed drastically across the years. So you can find here like a plot from 2010. So it was the beginning of the ResNet with AlexNet and etc. to 20. So I cannot see my screen, to 2024 with like the Gemini Ultra and other models, where now we use much more flops. And basically, like the beta lesson is that we need to use as much compute as possible, and we need to develop methods that can use as much compute as possible. A success of Transformer is that we are able to use much more compute than, for example, the previous RNN for language modeling, because we could simply parallelize everything and just maximize the amount of compute we use. So the question is that if we want to use as much compute as possible, what do we need to focus on? So here I'm showing a very simplified view that there's 3 axes you can work on. One axis is the algorithm innovation. So that's the most sexy axis. It's basically you invent like a new optimizer, a new modification to the architecture. So for example, the residual in a ResNet, the self-attention transformer, more lately, for example, the reinforcement learning from verifiable reward. So all this kind of stuff are algorithm innovation that can unlock new things. But all these innovation are meaningless without the 2 other axes. So it's more data. So we are now able to have like LLM and chatbots that are extremely competent, mainly because we are using the huge amount of internet data. So we want to have as much data as possible, and that data human generated is starting to stagnate. So maybe in the future we will have to do synthetic data. More data also means that it's not simply more bigger amount of quantity of data, but also like better high quality of data. So that's one axis. And another axis also to have simply bigger model. So for example, the whole ResNet in the ImageNet time, where maybe like 5 million parameters, which is not a bit ridiculous, given that now, like yesterday, Kimi released an MOE LLM transformer that was, I think, 1 trillion parameters in total. So you can see that from 5 million parameters 15 years ago to 1 trillion parameters, we just use a much bigger model. So my gist is like, to have a beta lesson, we do need the algorithm innovation, but we need to have much more data also. Now we are talking about trillions of data of tokens, of text token, and we are talking about trillions of parameters. All that requires to use just much more compute. So now we can first focus on the model axis. If I want to have like a model that is so big, how can I train it properly? If I take, for example, the Llama 3.1, which was 405 billion parameters, that was equivalent to more than close to 2 terabytes of 2 terabytes of data just for the parameters of the model. So you even in single chips, which is like H100, which is like a server grade and computer grade, like very high bigger than you could probably have in your bedroom. You cannot fit the whole model on a single GPU. And then if you want to fit also the optimizer, so for example, the Adam optimizer that's going to use twice more parameters, and then you need also to have more memory to store the activation and the gradients. So basically, very quickly, at some scale, you won't be able to fit your whole model on a single chips. And here I'm talking about a parameter that was less than 400 billion parameters. If I take the KIMI that was released yesterday of 1 trillion parameters, you will never be able to store it on a single GPU. There is some tricks, of course, to be able to fit those models on a single GPU. You can quantize the parameters, so meaning using a lower precision for those parameters. You can actually not store the optimizer on your GPU memory, but you can store it on the CPU memory, so optimizer offloading. Even you can offload a part of the actual model. You can do gradient checkpointing, so when you do the backward pass, you don't need to actually store all the activation, but you can recompute them as you do the backward pass, which come with the cost of slower, but reduce the memory usage. So there's many tricks to actually store a model on a single GPU, but they are all come with trade-off, of course, usually, which means that they are either more unstable or slower. And at some point, like, we want to actually use multiple GPUs in order to train a bigger model. So here I'm going to show very quickly two existing methods. You have first the pipeline parallelism, PP. So this is probably the most intuitive one. You're just simply going to split the model across the depth axis. So you're going to put one or several layers per GPU. So instead of storing the whole parameters on a single GPU, I will give the input tokens to the first GPU, which is going to process here the first layer. Then we output the tokens. We transfer it from the GPU 0 to GPU 1. So this transfer requires communication. And we do it until going to all the layers to get the output tokens. Here, the communication, and that's very critical. There is a lot of communication. So that's basically the whole activation on the forward pass and the gradient on the backward pass are going to happen in between each GPU. If those GPU are well connected, that may not be a problem, but we're going to come back to that. Then you have another solution, is the tensor parallel, where tensor parallel basically is instead of splitting the model per layer, you're actually going to put all the layers on the same GPU, but you're going to split the matrix multiplication, so the exact matrix, either column-wise or row-wise, across multiple GPU. So that's another way. Here you're splitting across the width axis of the model. Here, there's also communication during the forward pass and the backward pass, because you do a subset of the matrix multiplication on one GPU, another subset on another GPU, but then at some point you need to gather them back. And here there is a communication between the two GPU. This is for the model axis. Now about the data axis. The question is also we want to use more data, as I said previously. So the previous models, ImageNet, for example, was a few 100,000 images. Now we're talking about using several dozen of trillions of tokens. So if you remember the scaling laws, one paper from DeepMind in 2021, called the Chinchilla scaling laws, stated that basically to be compute optimal, you need for each neuron in your model to train with 20 tokens, so 20 to 1 ratio. That means that basically if I were to train a 10B dense parameter model, I will need 200 billion tokens. So this Chinchilla scaling law, people are not really following it anymore. People are actually overtraining their model much more. So for example, the Llama, which was 405 billion tokens, the parameters, was trained on more than 15 trillion tokens. That's a 38 to 1 ratio. And actually, if you want to train a very good small model, such as for example, the recent Hugging Face small LM3, which was a 3B model, you train it on 11 trillion tokens. So that's a ratio that is much, much bigger than the Chinchilla scaling laws. It kind of makes sense because you want to, when you have a small model, you don't simply want to be compute optimal, but you want to be also as powerful as possible in order to deploy it. In theory, the Chinchilla scaling laws say that you actually not train a 3B model for that amount of compute budget and token budget, but you should train a bigger model. But then if you train a bigger model, it's actually hard to serve on consumer grade, for example, GPU. So you want to package and to cram as much knowledge as possible on a very small model. So you're going to do much more overtraining, so a ratio that is superior to 20 to 1. The small model, small LM3, for example, it's 3B parameters, so you can easily fit it on a single GPU. That's very easy, even on consumer grade GPU. But if you want to train 11 trillion tokens on a single GPU, and thought you have to use a small batch size in order to fit all the activation and the gradients, it's going to take decades because you cannot have a big batch size. You're going to have to do several millions of steps, and literally you can just make the estimation based on the numbers. It's going to take you decades to train it. Of course, you cannot train a small model for decades because in 10 years, we will have a completely different kind of AI, maybe just AGI. So you need like a much larger batch size in order just to use as fast as possible, to train as fast as possible and to maximally use your GPU. But you cannot fit everything on a single GPU. So then again, you need to go multi-GPU when you want to train with more data. So here it's a bit more simpler than the model parallelism. Basically, everyone uses a variant of data parallel, DP. So here it's quite intuitive. You're simply going to take your batch size. So here we are talking about transformer, for example. So your batch size is going to be several seconds. So seconds, or there's multiple tokens on each seconds. And you're going to split each subset of the seconds of the batch size across a GPU, then another subset across another GPU, and etc. So we are splitting the batch size across multiple GPU. Each GPU holds the entire set of the parameters of the model. It's a copy on each GPU. Each GPU then going to do a forward. So you do simply all the forward activation to get the loss on each GPU, the loss that will be respective on the subset of the data that you have seen. Then we do the backward pass. So each GPU is going to compute their own respective gradients with their own respective subset of the data. And then we do a all reduce, where all the layers are going to communicate all the gradients together. So now you have all the same gradients on all GPU, and you can do an optimizer step and do the next step. So here, there's less communication in the end, like less frequent communication, as we are simply doing communication during the backward pass. During the forward pass, it's no communication between GPU. However, we can only do one step. So those methods are like completely orthogonal, and they can all be combined together. So in theory, you can do pipeline parallel, so split the model across multiple layers. Tensor parallel, split the model across the matrices, rows, and columns. And data parallel, where you split the data across the batch axis. Everything can be combined together. That's what people do in practice. There is different trade-off. So different trade-off, especially for the latency. So in tensor parallel and pipeline parallel, you have a much more sensitivity to latency than data parallel, where you can kind of overlap the gradient pass, backward pass with the all reduce. There's also different bandwidth requirement and different amount of frequency. All those things have trade-offs, and that's why also, like, usually when you have a big cluster of GPU, you have different level speed. I can have, like, for example, a bunch of GPU that are in a room, a bunch of GPU in another room. Inside a room, we have a high bandwidth. In between the two rooms, we have a lower bandwidth. Therefore, you could do inside a room only tensor parallel between those GPUs. And then in between rooms, where you have a slightly lower bandwidth, you could use data parallel. So there's also a whole hierarchy of bandwidth, which means also a hierarchy of which distributed method to use at which moment. This is the only what I'm going to talk about existing distributed learning methods. There is many other variants. So for example, there is a sequence parallelism. That's quite similar to data parallelism, but here instead of giving an entire sequence to a different GPU, here we're actually splitting across GPU the actual sequence. So across multiple tokens, we are splitting it. For example, for the feed forward activation, we can split, and we do feed forward on each different subset of the sequence length. And then we do all gather again when we have to do the self-attention. We also have the expert sharding. So when we do mixture of experts, where instead of having a single feed-forward network, we have multiple feed-forward network in parallel. Here we can actually shard the expert feed-forward parameters on different devices. So each device will have a single expert or multiple, and then we just gather them back at the end of the mixture of expert layer. And finally, we have FSDP, which is probably what most people use. You can look up at the literature. There's multiple variants of FSDP. It's kind of similar to data parallel, but also shard the parameters, and we do regularly null gather to get back the parameters when we do a forward. So that's a mix of basically doing model parallelism and data parallel, and that's kind of the way to go when people train their model. There's also other variants, so I'm not talking about everything. The Megaton paper explains quite well how do we do properly the tensor parallel. There is some slide detail to be able to do it correctly. Pipeline parallelism is very useful because you can, it's less sensitive to the bandwidth than tensor parallel. You can actually split your model across multiple locations. Unfortunately, pipeline parallelism has a problem of what we call bubble of time, is that when we do the forward pass, we are using all the GPU one after the other, and then we do the backward pass. But it's very hard to actually use all the GPU at the same time. So basically, the pipeline parallel will have for several seconds some GPU that will be idle and doing no computation. So that's kind of wasted, because if I give you a GPU, you want it to be fully used, to be always working, so that you really want to avoid idle computation. And the bubble of time is quite big. You can lose up to 15% of your time. There is some trade-off how to actually make it better. You can do micro batching, smarter order of the operation, or async backward pass. There's many tricks, but just to remember that pipeline parallelism is not the silver bullet because mainly of this problem. So here I talk about like distributed learning methods that were more like classical, so that's what people use, which is fine when you collocate everything together. So when you have everything in a single data center, for example, or if it's between two data centers but are very well connected with like a very high bandwidth, that can work. The problem is like if you want to actually do across the world, you're going to be bottlenecked, because all the distributed learning methods I showed you before, they require communication. You cannot simply split your whole AI training, either the model or the data or both, across multiple GPU and not have the GPU communicate. They need to communicate. That communication is actually can be several gigabytes or several terabytes of data that need to be communicated as fast as possible. If the communication is slow, we are actually waiting for the communication to finish. And while we wait, those GPUs are idle. They're not doing any work. And it's actually a very big waste of compute. As I said a bit earlier on, you just want to use as much compute as possible, meaning that your GPU should be always working. That's really the only thing you need to remember. So that's why people basically try to just cram as much possible GPU on a single location. For example, I think XAI with Elon Musk, they managed to put like 200K GPU on a single location, but they really struggle, and they had to have like some portable gas plant in order to have enough electricity in that single location. But it comes with a price. It's very hard to actually collocate all the GPU in a single location, because sometimes you don't have enough electricity on that location, as I said, for example, for the XAI problem. And you could build like more nuclear plant, for example, for data centers, but building a nuclear plant is going to take you 5 or 10 years. So it's actually faster to use multiple data centers at multiple locations where there is already enough electricity. But then you need to connect all the data centers together. You also want to do compute arbitrage. Is sometimes compute can be cheaper in one location than another, maybe because just people use less compute at that location for that moment. So you want to do an arbitrage and use that compute that is cheaper. Or maybe electricity is suddenly cheaper on that location. So the compute is also cheaper and you want to use that. So you will be able to split your model across multiple locations and use only the locations that are the cheapest for you to train your AI. And also you want to scavenge all the compute across the world. If you want to do a planetary computation, well, basically it's something where everyone could contribute in their bedroom their own GPU to a big AI training across the world. Here you will need to connect all those GPU, which have a very poor bandwidth in between, and be sure that they are always working and are not bottlenecked by that communication. So you cannot do it with the current methods. Data parallel, tensor parallel, and pipeline parallel, they will require a high amount of bandwidth, and you cannot do a planetary computation with those methods. The good thing about those methods is that fundamentally do not change anything about the math behind the training. So for example, if I do a data parallel and I'm splitting the data across multiple locations, I do a forward pass and a backward pass independently on each GPU, and then I do all gather the gradients, so the communication, or I do a communication, and then I continue my training. Whether I do that, whether I just train my AI on a single GPU or I train my AI data parallel across multiple GPU, the results will be exactly the same. The whole loss dynamics, the parameters, everything, except some numerical issues, you're going to get the exact same results. So it's very reassuring, because you can do tests on a few GPU, you saw it works, and then you scale it to maybe 200 GPU, so distributed, and you see that you're confident that as you do more distributed methods, it's not going to break, because it's exactly the same mathematical results. So it's very, very critical. Those methods are very attractive for that reason. However, I believe that we need to break away from those methods. We need to take more risky method that won't be mathematically equivalent, so that bring a risk, because it means that your whole learning dynamics, your loss, your gradients, and everything will be different, and they may get worse, but they will allow you to communicate much less and actually to do the communication across the world. So I'm going to show first two methods, two axes of methods for both the model and data, how you can actually break it and do planetary computation while going away from being mathematically equivalent. And then I will go to the third axis. So in pipeline, if you want to do pipeline parallelism across the internet, where, for example, each of us, we have a GPU in our bedroom, and we own only a layer of the model, and then we just forward through that layer, and then we send the communication to the other layers. So pipeline parallelism across multiple locations in the US, in Europe, in India, in Asia, everything. You can do it with Swarm. Swarm was a paper from a few years ago trying to do exactly this thing, pipeline parallelism across the internet, importantly with a bunch of heterogeneous hardware. So that's what you want, basically. For example, you have the T4 and the A100 kind of GPU, where they all communicate at different speed, which means you need to do some kind of balancing. Sometimes there's also like a failure both on the GPU, failure both on the communication. So you need to be able to route. If, for example, I did my computation on the first stage, so my first layer, for example, then I want to send to the second layer, my second stage, and one GPU, for example, the GPU has failed. You want to actually route the communication back to another GPU in order to forward. So it's actually quite complex in doing this kind of methods. And also, it's still going to require quite a lot of communication in between those stages. So you probably want to use some methods, such as, for example, more recently, the pluralist paper, where they do a compression. They compress the activation in pipeline parallel in order to use a pipeline stage across the world with a very low bandwidth. But this compression is very efficient in the paper, show there is barely any loss of performance, but still it's not mathematically equivalent, which means it brings with a cost, a risk. So that was for the model axis. Now for the data axis, you can simply use, again, data parallel. As I said before, in data parallel, each GPU is going to see a different subset of the data. They're going to do a forward with their subset of data, backward pass with their subset of data, and then they do a all reduce where they communicate each of them gradients. This all reduce is where the communication happens. The gradients are fairly large size, it's the same size as the whole model parameters. And then basically you want to compress the gradients. So usually, for example, your parameters may be in float 32, but you're usually going to communicate your gradients in bfloat 16. So it's twice less bits. So it's already a compression of time too, but that's not enough. So if you want to go across the world, and let's say you have a communication bandwidth that may be in the dozen or hundred of megabytes seconds, and you want to communicate a model that is like several gigabytes or several terabytes, you need to compress as much as possible in order to not wait for the communication. So there's, for example, three papers that are quite famous. Cocktail SGD proposed to combine multiple compression methods. So top K, you only take the top K values. Then the quantize. So I think you can quantize up to float 4, I think they do. So with only 4 bits per parameters. You can also do random specification. So randomly you drop some value. It's similar to a dropout, but here apply on the gradients. So that's quite aggressive, but they show that, for example, their throughput, so basically how much you can do a forward of token without being bottlenecked by the communication, as if you're bottlenecked by the communication, your throughput is worse. You can find that basically the all reduce, the classical methods, if you have a high bandwidth, it's going to be very efficient. But as soon as the bandwidth is actually very low, so maybe 1 gigabyte or less, the throughput is close to null, because with all reduce, you actually have to communicate a lot of data and you're just waiting for the communication. You're wasting time. While with Cocktail SGD, because they compress aggressively, they can still have a pretty good throughput with only 500 megabytes seconds. Of course, it's come with a risk because you're actually compressing very aggressively your gradients, and they won't be the same quality, and you may have a loss of ML performance. You also have PowerSGD, so it's kind of similar. You do another kind of compression. Here it's a low rank compression, so your gradients are usually low rank, so you can exploit that and to project them in a lower space. So instead of projecting a gradient that may be of size 1000 times 1000, you can project it to another space that's what I 1000 times 5, So it's going to be a huge compression factor, and you communicate much less data. It also comes with a risk, but it was fairly used at large scale. If you read the DALI paper, so DALI was like the first image generation from OpenAI, they actually have a big section in appendix where they describe OpenAI, how they use the PowerSGD. Maybe that's still what they use currently for GPT. And we have also DeMo, more recent paper, that's kind of similar. It's not a Laurent compression, but they use a Fourier transform-based compression, and they show that you can train also across the world in their networks. So that's also compressed quite aggressively. All those methods are compressed very aggressively, which come with a risk because you will never be able to get the exact same quality of gradients. The question is whether you can still get a good enough performance. So we saw one way to do distributed across the world, so with a low bandwidth, by doing, for example, a very hard compression of the activation in pipeline parallelism. For data parallel, we can do a compression of the gradients when we do the all reduce. So both of the methods are quite similar. Is in a way you want to compress aggressively what data you actually communicate. But it also means that in pipeline parallelism, so it's always like everything is in sync. In data parallel, everything also is in sync. So all the GPU needs to go at the same speed together, and they all have to be in lockstep. You just communicate less data, but they are still all going forward at the same moment in time. I argue that there is another axis that we should explore to do planetary computation that I think is much more efficient and can also be less risky, is to do local training. So I'm going to first come back to data parallel to explain how we can go from data parallel to local training. So data parallel, as I said before, you start with a model randomly initialized. You put the same parameters, a copy of the same parameter on each GPU. You do one step, so that's a forward, a backward, and you synchronize. So that's the all reduce. That's your bottleneck of communication. And then you do again a forward, a backward on each GPU with a different subset of the data. And then you synchronize again. So the problem is, as I said before, you have this communication that is very costly. So the cost, the amount of communication that we do, you can reduce it, as I showed before, with CocktailSGD, PowerSGD DeMo. There is a way to make it less costly, but it's still a blocking communication that you have to block for it, and you have to wait that this happens. So you can compress as much as you want, but if the bandwidth starts to get way too low at some point, you still have to wait for the communication, and you have idle GPU waiting for communication and just wasting the time to do another computation. So there's a way to do local computation, local training. There is a lot of literature up to the 1983, I think. It's come under many names, such as local SGD, federated learning, although it's slightly different, and I can argue later why. And FedOPT. Here, I'm showing in my framework, which was made explicitly for LLM, DiLoCo. So where the idea where we still have, we start with the same model, randomly initialized. You put the same copy of the model randomly initialized on different GPU, and then each GPU is going to see a different subset of the data. The difference is here, like we don't communicate at every steps, but we do multiple forward, backward pass on each GPU, and then we apply, we do an optimizer apply, so we update our parameters, but each GPU with each replica, which are different subset of the data, is going to be optimized in a different way because they see different data. So now you don't have a single version of your parameters, but you have multiple versions that are slightly different because they are training on slightly different data. So they're gonna all do multiple steps. So that's between dozens to hundreds of steps. They're gonna do differently. So the model are gonna be slightly different, but there is no communication in between. And then, every, for example, 100 steps, you're going to communicate all the parameters together, so to resynchronize again them together, and then you do another round of local training. So the idea of local training is like you do multiple forward, backward steps and optimize or apply without communicating. Of course, like you're going to say that if we are communicating much less, so here we're only communicating every 100 of steps and we do local computation, we are bound to get lower performance because intuitively you want to communicate as much as possible to get the best performance. And that's true. In order to recover the lost performance because of the less communication, we need to do a step of outer optimization. So it's inspired from the local LGD FSDP literature. There is many small variants that are all quite different. I'm showing here like the variant of DiLoCo, which was the best for LLM training. Was there a question?
We can take questions at the end.
Okay. So here I'm showing the variants of DiLoCo, which is a variant of FSDP local LGD, but that's the one who works best for LLM training. So you have two steps of optimization. You have first in red the inner optimization, which is the local training, where each GPU, so each GPU is a worker with an index of I, is going to see a different subset of data. So that subset DI, they're going to compute their loss here on line 6, and then on line 8, they're going to update the parameters with their inner optimizer. So the inner optimizer is going to be Adam. And they're going to do multiple steps each independently to optimize their parameters. And then once in a while, so every, for example, 8 steps, which could be, for example, 100 steps, they're going to compute a delta. Here it's a delta between, for a given parameter, for a given worker, a given GPU, their current parameters minus the parameter they had 100 steps in the past. So what you can see is basically this delta in the parameter space is a trajectory. Is what's the path you took across hundreds of optimization steps. This trajectory, then we can consider it as a form of outer gradients, although it's not a proper gradient. You have one outer gradient per GPU, per worker, and then you do an average. So here, this average in line 12 trigger an all reduce operation. So that's the communication. That communication only happens every 100 of steps. So while this communication is very costly, you amortize it. And then you do a now step of outer optimization. So you actually consider that these outer gradients, which is, as I said, not a proper gradients, you actually act as it was a proper gradient and you apply an outer optimizer. In the FSDP literature, there's many kind of optimizer they use, sometimes Adam and everything, but we actually show in DiLoCo that for LLM training, you actually need to apply a much simpler optimizer, so Nesterov. So it's LGD with a Nesterov momentum that actually works much better. And if you combine basically as inner optimizer or powerful optimizer such as Adam or Muon, for example, and outer optimizer using Nesterov, you will be able to train for local training, so not communicating for dozens to hundreds of steps, and yet at the same performance. So the problem is like with DiLoCo is like you do less frequent communication, so that's good, you can amortize it. But when you have to communicate, that's still a very costly communication. Because you communicate the whole parameters, and it's also blocking operation. So you only amortize it, but you don't fully resolve the problem. So you can do another solution, which is a streaming DiLoCo. You can consider that your model is actually split across multiple layers. All the layers could be on the same GPU or across multiple GPUs, that doesn't matter. And you have like the whole model on different GPUs, still as before. They're going to do multiple steps of local training as before. But when you synchronize, you don't synchronize, so with the outer gradients, you don't synchronize the outer gradients for the whole parameters, but only for one layer. So you have the layer green of the parameters. So if you have, for example, 3 layers, here we're only synchronizing every 100 of steps, 1/3 of the parameters. So that's a massive reduction of memory, of communication. And the next outer steps, so after another 100 of steps of local training, we communicate the red layers. So the good thing is, like, as before, it's a less frequent communication because it's only once in a while. It's also less costly communication. That's a way to actually do a form of compression as we only communicate a subset of parameters, but without any loss of ML performance that we found in practice. But that's still blocking operation. So then we can do an overlapping where the idea is like when we communicate that outer optimization, we don't actually block. So once in a while, we do 10 local training steps. We compute the outer gradients for the layer green. We communicate it, but then we don't actually wait for the communication to finish, but we still continue to do local training, and then we replace it. So you can find on this algorithm, the way we do it is very similar. Every 8 steps, we're going to send the communication in line 8 of my parameters, or my green parameters, for example. And then in those steps in the future, we're just going to get to receive that communication, meaning we can fully overlap the communication. The good thing is like if you can overlap the communication with the computation, it means that if your model is actually very long, very slow to take a step when you do the forward and backward, very slow to make the computation, you have actually more time to do the communication. So the slower your model is, the more you can overlap communication. Luckily, larger model also usually have a longer step time. They just have more parameters, more flops, more data to do. And first, even though larger models have more data to communicate, they also have a slower step time, and first it's easier to overlap more communication. So we show here, for example, the bandwidth required to achieve an 85% compute utilization. So compute utilization is how much time is dedicated to fully doing computation versus doing communication. You want that number as high as possible. For data parallel, with a 1B model, it's like in the 200 gigabytes seconds, while DiLoCo is like 2 orders of magnitude less, 200 gigabytes seconds. But as you go to a 10B model or a 100B model, the 100B model is going to be 100 times more data to communicate. And you need more time, actually, more gigabytes per second for data parallel to communicate. But for DiLoCo, streaming DiLoCo with overlapping, it will require less bandwidth, only 1 gigabytes, because you can fully overlap the communication, and the model is actually much slower. So we have more time to overlap. So here, like in this example, for example, this communication, this outer gradients that was only a single layers, so streaming and overlap, was also quantized to float 4, and we found in practice there was no loss of performance. But you can further reduce that communication. For example, MuLoCo and DiLoCo X, two recent papers made by not my group. They apply, for example, PowerSGD or DeMo. So the compression method we saw work well for data parallel. You can also apply it on the outer gradients in streaming DiLoCo. So you can further reduce that thing. As I said before, all those methods are not mathematically equivalent. So data parallel and pipeline parallel are mathematically equivalent to just train on a single GPU. And those, they are safe. You can trust their results. While our methods, they're going to change the learning dynamics. You do an outer optimization steps. You only communicate a subset of the parameter, etc. Meaning that you don't have the same exact learning dynamics, the same model optimization. So you can be scared that it actually doesn't work as well. And yet we see that, for example, streaming DiLoCo, if you train, for example, for 200 billion tokens on data parallel versus streaming DiLoCo, if you were to only have 1 gigabit seconds communication between your GPUs, you will take 1,000 hours for data parallel, while only 8 hours for DiLoCo. And yet you can find that the performance on both the loss on some downstream evaluations such as LSWAG, TK, RKZ are roughly similar. So you can be not mathematically equivalent, use much less communication, and yet be still performance equivalent. So now, like I'm showing you like methods that I know work well at scale. For example, DiLoCo X that was published by another group in China show that we can make it work this model at 100B parameters. So we know that we can make no communicate much less. So does that mean we can do planetary computation where you have GPU all across the world and they can all train the same big AI, just decentralized? So not exactly. So while the bandwidth is, I think, a solved problem, you see more papers that try to compress even more those outer gradients and everything, but it's very incremental in the sense that we already solved most, I think, of the bandwidth problem. We have another problem, which is the hardware failure. Llama 3 from Facebook, so that was like the previous generation last year, they reported that the error failure rate over a 16K GPU and 45 days was quite high. So they had one failure every 3 hours. They were using data parallel. When you have a failure, in that case, one GPU fall, it means like you are actually blocking the whole cluster is falling down, and you have to reconfigure it to not use the GPU. So a failure on a single GPU is very costly. And the problem is like if you have like the same infrastructure, if you have twice more GPU, you're just gonna have twice more failure potential, and etc. So it's gonna become exponential, and the more GPU you have, the more failure you have. And here Llama was using enterprise grade GPU, and they have a whole infra team to actually make sure those GPU are trying to not fail. If you want to do planetary computation using consumer grade GPU on your bedroom, it's probably not well taken care of, and your GPU is going to fail very often. Maybe every weeks or every month, your GPU is going to fail. But if you use hundreds or thousands of GPUs, it means that basically every hour or every 30 minutes, one GPU is going to fail and bring the whole training down. It's going to bring the whole training down only maybe for a few minutes, the time you reconfigure on a cluster. But if you have too much failure, it's going to take a very big hit on how much GPU and computation you can use. So you want to be resilient to those failures. In streaming DiLoCo, and I think in local training in general, local training is quite an attractive method because each you can replicate your model across multiple locations, and each of them are going to be training independently. So if you have a failure, it's localized to that local training bubble, and you can avoid it. You can avoid to put down the whole cluster. Furthermore, you still need to do communication, but that communication is very rarely, every hundreds of steps. So maybe you can recover that failure quite fast enough to then come back and do the synchronization. And because we overlap, we can have like some kind of a graceful period where we can try to recover from that failure during that thing. But there's also another problem is like if your GPU, especially if you use heterogeneous setting, so if you use, for example, H100 and A100, two kind of different GPU, they don't go at the same speed. So even in that setting, you still at some point have to blocking communication in streaming DiLoCo. At some point, you still need to all wait for each GPU to communicate their data. And basically, everything is going to be slower. We're all going to wait for the slowest GPU, which is not really what wanted, because if you have a better GPU, you want to still use it and not wait for the slowest. So then you need to go to other methods. We had a paper a few years ago, 2 years ago, 1 year ago, async DiLoCo, where basically we do a delayed outer update. I'm not going to go too much into details. The idea is like we saw that we don't want to wait for the other replicas. So basically, we're going to synchronize as soon as the replica finish its dozen of steps of local training, it can communicate with its parameter server and never wait for the other replicas. The problem is mean that different replica will synchronize with the parameter server at different moments in time, and they don't really bring the same information. One replica may be several hundred of steps in the future compared to the other ones, and you have like a problem of consistency in between different replica. A way to do it is basically we don't update our outer optimizer state at every synchronization point, but we try to have a buffer where we accumulate multiple outer gradients from different replica, different moments in time, and we only update it once in a while. So this kind of delayed update, I'm not going to go too much in detail, allow us at a small scale, only 150 million parameters, to show that we could do async DiLoCo where we don't have to wait for the slowest GPU, which is a very desirable property. So the question is like, no, can we do planetary computation training across the world? Not really yet, because I think bandwidth, as I said, is not really a problem anymore with those methods. Async DiLoCo might handle most of the hardware failure, although we will need to publish or someone need to show it that it can work at a very large scale, which is always a risk, of course. As I said, like DiLoCo has been proven by Prime Intellect and then by China Telecom, I think, the company, at 20B respectively and 100B that we show we could scale DiLoCo. It was a synchronous version. No one has proven externally on open source that async DiLoCo could still scale at a larger scale. But we have also another problem, is how many replica we have. So while in data parallel, which is a mathematically equivalent method to a centralized training, if in data parallel you split your batch size across 1 GPU, 2 GPU, 4 GPU, you have the exact same results. So you're completely agnostic, ML-wise, to how many GPU you do distribute your computation. So that's good. If you have more GPU, just use more GPU and your model will still be the same, just faster. However, in a method like local training, FSDP, or DiLoCo, you're actually very sensitive to how many replica you have. So how many different subsets in parallel that do local training. And that's, I think, something I'm quite frustrated about federated learning, which was a field before DiLoCo. They did hundreds or thousands of replica, but they actually never really care that if you have thousands of replica, you're going to have to use much more flops in order to be ML-wise performant against a centralized baseline. However, when you go at a very large scale, when you train an LLM, for example, like Kimi, which is 1 trillion parameters, flops, it becomes very expensive. We're talking about millions or billions of dollars. In that case, you want to be your method to be as flop efficient, meaning that if I give you a certain amount of flops, you need to be able to produce the same performance as a centralized baseline. In our case, if we have DiLoCo with 2 DiLoCo replica, so you split your whole training into 2 replica, and you use as much flops as a centralized baseline, just to communicate less and you're asynchronous, you will be able to be as good ML-wise as a centralized version while not being mathematically equivalent. So that's good. But then if you go to actually more replica, to, for example, to 4 replica, 8 replica, or even more. So as we show in this paper, the scaling law for DiLoCo, that the more replica you have in parallel, that do in parallel local training, while being, importantly, ISO flops, so you're using as much flops in the overall system, you will be worse than a centralized baseline. And that's actually a problem, because if you want to do isolate the failure as much as possible, you want to have as much replica as possible. If you have only 2 replica and there is a failure, you isolate the failure only in half of the cluster. If you have 8 replica, it's only 1/8 of your cluster that's going to be affected by the failure. Moreover, if you want to do actually planetary computation, so using all the GPU in all the bedrooms in the world, that's going to be between a few thousand, maybe millions of GPU that are all different at different locations, all very low bandwidth in between and can have failure. So you will want ideally to have like millions of replica in parallel. But if you do that, you can still train your model. It's just going to be extremely inefficient, and you will require to put much more flops in it to get as good performance as a centralized baseline. And which I believe you really need to be ISO flops to use as much flops, because to train a very large scale model, flops become very costly as you need order of magnitude less than it was before in the past. So can we do planetary computation? So with local training paradigm, which I think is the future to do pure distributed / decentralized learning, and the DiLoCo family of model, which has proved its work quite well, we are now competitive ISO flops against a centralized baseline when we have 2 DiLoCo replica. We use several order of magnitude less bandwidth than a centralized baseline, which is desirable property. We can fully overlap the communication with computation, which is even more, we can overlap even more computation as the model is slower, which is nice. And we show, for example, a paper external to us show that we can scale DiLoCo up to 100 billion parameters and still being as good as the centralized baseline. There is some work we did on asynchronous training. Other work also in the federated learning literature, but that's less on LLM training large scale. So there is not really yet a published work on a large scale LLM that show that we can do async DiLoCo, async local training very well. And furthermore, there is not yet a work that shows that we can scale to 8 or 16 replica for LLM while being ISO flops and as good as a centralized baseline. So that's something to explore. But I believe that is bound to happen. People ask me, oh, can we do planetary computation right now? Not really, because of the problem I said before, but I think we are very close. A lot of progress has been made recently. And it's bound to happen that at some point we will be able to do planetary computation. I'm putting here a reading list, so I will send the slide and we can probably put on the website if you want to have the links. I recommend the first 2 books, which are how to scale your model using classical distributed learning method. Classical, I mean, because they are mathematically equivalent to a centralized baseline. They are not as good to actually use less bandwidth or be asynchronous, but they are safe method. And then I'm showing here like a few relevant papers for local training for large-scale language model. In particular, PyTorch now implemented streaming DiLoCo in their own code base, so you can reuse that if you want to experiment. And likewise, Tsam on Twitter has made a NanoGPT, a version for DiLoCo. So NanoGPT is a very small GPT LLM training that's very easy to tune, that's very easy to train. You can train it, I think, in a few hours. And you can quickly experiment new idea on top of NanoGPT and DiLoCo. So that's it for now. So that was a presentation how to do planetary computation. I first show existing classical methods, which are mathematically equivalent to a distributed to a centralized method, but they use a lot of bandwidth. They are lockstep. Each GPU has to be synchronized to each other at the same moment in time. Therefore, I believe that to do planetary computation, you need to go beyond that. But you will have to take risk. You cannot be mathematically equivalent to a centralized baseline. And we have to prove that we can still train your model across the world while being ISO flops, meaning using as many flops as centralized baseline, and be as good while bringing much more benefit, such as less bandwidth and resilience to failure. If you have any question, I can take it.
So there are a couple of questions in the chat. If you see the bottom,
yeah, let me see.
And go to Q&A.
I cannot. Can you? Where in the message of the call? I don't see the chat.
In the bottom right, there is 9 dots column with meeting tools.
Okay, I never use Q&A. Okay, when data goes from one GPU to a second GPU, does it need intermediary CPU? Can you go directly? Oh, I lost my light. When data goes from one GPU to a second GPU, does it need any intermediary CPU, or can it go directly, and is it fast? It's kind of depend of what kind of bandwidth you have. If you were to go from one GPU to another GPU and they are in the same cluster, usually you can connect them interconnected, so you don't have to transfer the data from the GPU to the CPU, then to the other CPU, then back to the GPU. You can go directly. There is interconnection. For example, if you use TPU, you can simply do using the ICI communication to go straight. However, if you want to communicate over the internet, like across, for example, different countries, your data from one GPU to another GPU, you will have to go to the CPU memory and then to actually transfer it. So it depends to how far you are going. Abira, do we use multiple GPU if a model is too big? Yes. If your model is too big, you have to use multiple GPU. In the case of local training, here I'm only showing a way to actually distribute the data axis, but each local replica in local, which different subset data, can use internally, for example, classical tensor parallel or pipeline parallel. It does require those methods that you need to have the whole model in a cluster that is highly well connected. However, then each cluster can be poorly connected in between. Next question. When training process is broken down for multiple GPUs, do all GPU need to be a similar configuration compute power? Yes. When you have like multiple GPUs, especially in like classical methods, which are like not async, you need to have all the GPU to have the same configuration and same amount of power. Basically, they need to go as fast as possible and at the same speed at each other. Otherwise, we're going to have to wait for the slowest. So you need to have the same configuration and the same amount of power per GPU. That's also why if you use a classical distributed method, you want to use heterogeneous hardware, which have, for example, H100 versus B100, which have different configuration, different power, different speed. You're going to be very bottlenecked by the slowest GPU. Next question from Vibro. Does overtraining not lead to overfitting of the model in case of like small LM3 where the ratio is 3.6661? No. So the problem is like you probably learned about overfitting, underfitting, and everything, which was, I think, very important on generalization, where you do the trend validation test set. What's very important in the previous setting, the first vague of deep learning, when it was a small model. Now we are in a new kind of setting where basically you are training a model that is so big and you on so much data that it's actually very hard to overfit. You could overfit, but even at that small scale, the model is only 3 billion parameters. So when you see 15 trillion tokens, but that are very diverse, they're not coming from a single domain, but from all over the internet, you have so much diversity of data that actually you don't overfit on that kind of setting. And the hope is actually you actually can just generalize and use as much flop as possible. So it's quite different setting from what we used to learn in classical deep learning. A question from Aaron Margolis. Regarding 20-to-1 scaling law, do regulation techniques such as dropout and pruning reduce the number of needed tokens? Not really, because like if you want to do regularization like dropout or pruning, so in the case of overfitting, if you actually use less or that, it's kind of, I think the same question as before. We don't really overfit right now. You could overfit if you have, like, for example, let's say a 20 trillion parameter model and you have as much data or something. Here you could overfit, but because we just increase massively the amount of data while the model is still quite small comparatively, it's actually very hard to overfit. So you could use a relation technique in case of overfitting, but that's not about reducing the number of needed tokens. The idea is you still want to see as much token as possible, always more, and you can combine it with a regulation technique to avoid overfitting, but you still want to see more tokens. That's not a solution to see less tokens. Anonymous. Iliad Sutskever said pipeline parallelism is not good. Do you have any insight on that? I think it's kind of a question of vibe. Some people like to do pipeline parallelism. Personally, I hate pipeline parallelism, so I would agree with Ilya. The problem with pipeline parallelism is like first you have the bubble of time. So you can just Google this thing, is like how you actually have to communicate. Basically, you do one computation of one layer per GPU for the forward pass and for the backward pass. But then basically you always have some GPU which are idle. That's quite annoying about that. So they are wasting computation. And there is some tricks, but it's very annoying to actually use as much computation as possible in pipeline parallel. Another problem also with pipeline parallelism is like they are not very great, I think, for fault resiliency. If you lose one GPU, then basically you do a forward and then you want to do the backward, but one GPU has crashed. So you cannot do the backward anymore because you lost one node in your backward pass. So it's actually very poor for the resiliency. Of course, that's my view, and maybe Ilya Tuskever view, but other people, such as, for example, Pluralist AI, so it's a company in Australia who try to do distributed pipeline parallelism, they believe it could be working. So I don't think there is a proper consensus on that question. Question from Arsh Karyam. Is there ever an upper cap on how many GPU should be used for a particular size model? Do we ever see a drop in training efficiency or effectiveness by using too many GPUs? Yes. So first of all, if you want, in let's say in classical distributed method, you will do scaling laws. You will show that I have that amount of flops budget. So how many computation I need to do, or I can do in a given time. I will then choose based on my scaling laws. So you can find, for example, in the Kaplan paper or the Chancellor paper. I actually need to train a model of 10 billion parameters. I need to train on 1 trillion tokens, for example. And then you can actually use as much GPU as possible to be as fast as possible. If you use too little GPU, you're going to be slow because you cannot distribute as much as possible. If you use too much GPU, you could also be slowed down because your GPU are not fully working. So if you use too much GPU, you don't have enough, for example, in data parallel, you don't have enough token per GPU. So they're not using their full power of computation. And they're actually spending more time on communication, and your MFU is going to be quite low. So that's a whole trade-off, and it's actually quite complicated to find the right configuration. And if you look, for example, at the Llama paper, their MFU, so basically how much percentage you're actually using the computation of your model was very low. I think like in the 10 or 20%. Anonymous. Your PhD was on control learning and computer vision, but you're currently working on distributed modular LLM. Are those two areas of research connected in some way? If not, how do you move toward distributed modular LLM research? So that's a good question. So my PhD was on control learning, computer vision. So like, for example, you take ImageNet, you learn 100 classes, then you learn 100 new classes, and etc. You keep adding new knowledge. I think control learning is still critical for AGI. That's probably the most critical thing. However, when I joined DeepMind, we thought that we wanted to do modularity. So actually how to have a modular system where you have different components learning different kind of knowledge. So that could be a mix of experts, but that could be also something else. We believe this is very useful and probably needed for content learning because you can compartmentalize your knowledge on different locations explicitly of your model. That's probably a desirable property. However, we also wanted to be collaborative, where everyone across the world can contribute their own module inside a bigger AI. But then I realized that you need to do distributed because all those modules will be across the world, so poor connection. And if I contribute to my module, you contribute to your module, and etc., we don't contribute at the same speed. There's many problems of infrastructure. You will have to distribute it. So I saw that we will first need to solve a proper distributed learning, and then we will be able to do modular LLM continual research. So I'm not doing content learning anymore, but I hope to come back one day when distributed is fully solved. Neaf Asif. How do we ensure the security and the integrity of data over such a large network of GPU? That's actually a very big question. So if you own all the GPU, they're just, let's say like I'm just renting GPU on Google Cloud. Some of them are in the US, some of them are in France, some of them are in China or whatever. Here, like I'm owning, or at least I'm leasing the GPU and I own the data, so there's no security risk. If I do planetary computation where I'm using all of your GPU in your bedrooms and everything, I need to be sure that no one is going to falsify the data or the gradients during that planetary computation. and that's actually a problem. There's people who try to make some solution. It's not really clear how to do it, and I think that's a big challenge. And it will probably come with an inefficiency in your training. So I don't really have a solution for that. Shamima Hossein. Is there any rule of thumb for knowing when we might need data or model parallelism and how many GPU we might need? So I think like it's a lot of trial and error. You can have like so first, like I think in the you should look at those two ML books, especially the first one is quite nice. It gives you like some kind of rule of thumbs, like how to actually in your head like estimate what are the communication, how much you can fit in a single GPU. So that's a very good link. But otherwise, you want to minimize communication as much as possible. There is a different amount of, as I say, hierarchy of distributed method based on the communication. Data parallel is going to be using the least amount of communication. Then you're going to have like maybe sequence parallel and then maybe model parallel. So like for example, tensor parallel. So ideally, if you can fit your whole model on a single GPU, and then you just do data parallel, so you replicate the model across multiple GPU, that's perfect. You want to avoid doing model parallel if you can. If you really have to, try to minimize as much as possible. So in general, it's a lot of trial and error until finding the right setting for your model given your configuration and seeing whether first it can fit, and second, if it can be as fast as possible. Timur Karisov. Are there any efficient implementation for doing ring-based all reduce on sparse compressed gradients? I'm not sure exactly about that. There is probably variance. I think you probably need to look at the PCCL. I think like Prime Intellect released recently a library to do a new protocol to do, I think, a better all reduce in that case. So maybe that could be a good direction. So just Google Prime Intellect PCCL. I think that should be a solution. Unfortunately, in Google, we have our own implementation, which may not be public, so I'm not exactly sure what exists outside. Sahad Nasir Bahir. Can we have the presentation slide after the class? Yeah, I will send the slide to Ahmad, and you will maybe put on the website or the YouTube link. Samina Hossein. Can you recommend some paper for beginner that describe the internal of parallelism so we can implement them? So I will strongly recommend to go over the two books, the GDM How to Scale Your Model and the Href Ultra Scale Playbook that show like classical parallelism method. You can also look at the Picotron. So from Hugging Face, Picotron, they have a small toy code base and also a YouTube channel where they do from scratch, implement from scratch distributed methods, and you can learn that way. So Google Picotron from Hugging Face. Amit Prakash. What kind of errors are these GPU error for the Llama 3 run? GPU fail in some, so there's many errors. That's a good question. What's the errors? If you look here, basically they show like a list of the failure. Sometimes your GPU fail, sometimes it's memory will fail, sometimes there's software bug. So there's always software bug. Sometimes it's software bug like that. Maybe the PyTorch has a bug, but it could be also maybe somewhere in the networking stack or the CUDA kernel or something there's a bug. There is sometimes like a problem on the actual connection, so network switch cable, the connection between GPU, there is a fail. It's hardware, it can fail. Sometimes it can be too hot the GPU. Sometimes it's actually like the SSD, so like the CPU. You can have problem everywhere. That's such a complicated system where you have so many moving parts that you will always have a failure, and it's always will be new failures. So you cannot completely eliminate the failure. So luckily, Facebook has a lot of software engineers, and they can try to make it as good as possible, but you will always have new failure for every new run. Anshuman Singh. So the current best planetary computation is still limited to 100B parameters. So I guess the biggest one that is public is probably this one, I think, yeah. I'm not sure there's a bigger one. But it's not limited to 100B parameters. There's also like to do planetary computation, but you still need a lot of GPU. Whether even if it's planetary wise, you still need a lot of them, and no one has shown publicly that you can do more than 100B. But if you can make it work at 100B, I'm pretty confident you can make it work at bigger scale. Anonymous, will there strictly be a need for planetary computation? Do you think there is a possibility of algorithmic innovation that is more data and more efficient? So there is always like new innovation. For example, if you look at the DeepSeek paper, they make a lot of innovation on the transformer mixed of expert architecture, etc. Every like big labs also make a lot of improvement, algorithm innovation. So you can be much more efficient, meaning that if for the same amount of flops you put in your training, you get a better model with those algorithm innovation. But then you also want to use more computation because it also will be better. So I think it's like it's a mistake to put in opposition the algorithm innovation and the computation. Those go in pair. You want to be as algorithmic innovant as possible to be more innovant per flops, but you also want to use much more computation. Maybe you could actually solve AGI by just making work on one GPU, but we are not really in that paradigm. The current paradigm is still to use more flops. Amit Prakash, in the final reading list, you showed the JAX-ML book. Does it all the same for PyTorch and GPU in general, or mostly JAX and TPU? The book was quite, so this book, the book GGM How to Scale Your Model is mostly targeted for JAX and TPU, of course, but a lot of things are very similar to GPU. Is like you do the data parallel or pipeline parallel in GPU or TPU is the same thing. You still have to do all gather, all reduce scatter. Those operations are very agnostic to the hardware. A lot of heuristics are the same. So I think you can still read the book and that will still be very relevant for GPU. You will have a bit more detail about TPU, but that's okay. And you can just go to the next link, so the Hugging Face Ultra Scale Playbook, which is more targeted to PyTorch and GPU. Anonymous, any Python libraries to start parallelism for beginner? Yeah, use Picotron. I should have put it in the link. I'm putting here in the chat, Picotron, Hugging Face. So Picotron from Hugging Face is a good way to learn parallelism on a very toy code base. Vibor Kumar, maybe not a very answerable question. Okay. But what's the intuition behind training with distributed training, which is not very mathematically accurate, but still end up with similar results as collected, mathematically accurate training? So basically, why like methods such as, like, for example, streaming DiLoCo, which communicate much less often, communicate only once in a while a subset of the parameters that is overlap and everything, quantize and everything. Why does it work as well with two DiLoCo applicants at quite large scale as a centralized baseline? There's multiple factors. So when you communicate the outer gradients, this trajectory is actually quite well behaved. It's like much more smooth and less noisy than the gradients. So when you apply an outer optimization step, it's very critical. You can actually do a big jump in the parameter space that can recover most of the mistake. The question is like why instead of, for example, in the literature of federated learning, people keep doing the inner optimizer SGD and then outer optimizer maybe Adam. That was a mistake. So you need to have a powerful local optimizer to train a transformer, such as like Adam or Muon. And in the outer optimizer, we actually show that we need to have a Nesterov. We don't fully know yet why that works better. We have some intuition, but nothing concrete yet, which, as many things in deep learning, also it's very hard to pinpoint exactly the reason why. Luisa Corpasi, what's your estimate of planetary compute power of the world as of today? Very good question. So I cannot reveal the numbers of Google, but you can look online probably of how many GPU are owned by OpenAI, Microsoft, Anthropic, etc. XAI. You can probably look at Semi Analysis. That's a blog about those kind of data center explanation that give how much power is for each thing. Then you have the personal GPU. I believe that right now most of the computation is still located into the corporate enterprise-grade data centers and not in the personal computer. So I don't really have a number to give you, both because I'm not sure I can give my numbers and I don't also know the other people numbers. Nest map system. For training across GPU distributed across the world, is data parallelism the only option, or can we have other parallelism as well? You can have other, like I show, for example, pipeline parallelism. People like Max Rabini, who did Swarm, and then you have the pluralist startups who pick up Swarm and make a compression in between the pipeline stage across the world. You can use pipeline parallelism across the world. Personally, I don't think that's the way to go, but there is research in the direction, and they have pretty good results. So that's not necessarily data access. Yadnya Shakane, what's your thought on Prime Intellect 1 and Intellect 2? So Prime Intellect is a very strong team. Intellect 1 and Intellect 2 are very different things. Intellect 1 is basically open DiLoCo, which is open source version of DiLoCo that they trained, I think, on 30-ish replica, and they quantize the outer gradient in FLE4. That was a good reproduction at 10B scale with 1 trillion tokens, so pretty good model. Unfortunately, they didn't compare against a centralized baseline, so it's hard to know how much inefficiency they had in their system, but also costly to train a model at that scale. Intellect 2 is very different. Intellect 2 is actually a way to do offline policy training for the post-training. So here I said in this talk, I'm only talking about the pre-training, because the post-training, where you do RL and you do the RLVR, so reinforcement learning from verifiable reward. That's a very different kind of distributed system where you have like sampler who are sampling reasoning traces and then are sending back to a learner that actually batching it. It's a completely different way. Both are very interesting, and I think both are the pre-training and post-training are needed. So my thought is that Intellect 1 and Intellect 2 are very cool. And there are the two parts of the training, one for the pre-training, one for the post-training. Wasif Wahid. What are the pros and cons of using pipeline parallelism technique for distributed training in machine learning? Pipeline parallelism can use less bandwidth potentially than data parallel under the right setting. It, however, requires to have like quite a large batch size because you need to do micro batching to avoid as much as possible the bubble of time. The bubble of time means that it's very hard to not have a bubble of time. There is a paper from ICLR last year, I think, called Near Zero Bubble Parallelism. We try to show that you can reduce massively the bubble parallelism, but you will still have a little bit of bubble of time, meaning like an efficiency in a pipeline parallel where your GPU will be idle and close to not doing computation. So that's the main con of pipeline parallelism. The second con I said before is that I think it's less easy to deal with under fault and hardware failure. Taratra, sorry. In your experience, what are the most robust approaches to distributed learning? Setup that remain effective under set conditions like intermittent network failures, no dropout, and silent GPU failure. I believe that you need to do local training, meaning that you need to fit your whole model on a single location. So your whole model may be on multiple GPU, but they're all well connected. And then you have multiple clusters across the world that do local training. So they are completely independent and once in a while communicate. I think local training is the way to go if you want to do a worldwide planetary computation. Taratra again. Do you think there is a specific algorithm or architectural choice that help distributed training be more resilient under this kind of issues? So if we talk about bandwidth, if you have like a smaller model, for sure it's going to be better. For example, if you use MOE, for mixture of experts are great because like you only activate, maybe like if you look at the Kimi that was released yesterday, for a given token, they only activate 30 billion parameters, so only. But the total amount of parameters is 1 trillion parameters, meaning that yet they activate little parameters, so they are very efficient, but they also have a lot of parameters that when you do the all reduce on data parallel, you have to communicate much more. So if you have a very low bandwidth, using a mixture of experts is going to be much more harder than using a dense parameter that is much less parameter hungry. So there is some kind of architecture choice like this you can deal. Also, mixture of experts, there is communication you have to do when you do expert sharding and etc. but then for the hardware failure, you will always have hardware failure regardless of what you use. Hardware failure will happen anyway. It's both of which kind of hardware you're using and how many chips you're using. I'm not sure I can ask some more of these questions. It's a bit too vast. Luisa Corpacci, are you aware of a tool that estimates GPU requirement based on data and model tag and chef usage task tag? No, I don't. I'm not aware. It's not that hard. You should look at like the first thing I think, like using rule of thumbs. If you know a model is like, for example, like the small LM tree is 3 billion parameters, so you can estimate very quickly how much it actually costs to store it in on a GPU. So it's going to be 3 billion parameters multiplied by 4 to store them, to have them the amount of parameters in float 32 that you have to store in the GPU. Then you actually multiply this by 3 to get the amount of memory you need for the model and the optimizer, so, such as Adam. And then you can estimate like the activation and the gradient based on what's your second length and your batch size. So you can make like rule of thumbs to very quickly estimate whether you can actually fit the model or not on a single GPU. And then if you do sharding, for example, tensor parallel, if you do tensor parallel across 2 GPU, you just divide the amount of memory per GPU par 2. So it's quite easy. PM Salman Khan, how about HF Accelerate help in doing distributed training in a node of 6H100? I'm not familiar enough with Hugging Face Accelerate, but I think they provide like utilities to do data / pipeline / tensor parallel. So yes, it will help you to do distributed training on node of 6H100, which are well connected in between. If it was 6 GPU that were like across the world, they're poorly connected, then HF Accelerate won't be any use of. Anonymous, a little off-topic question. Can you give some guidance on how to study feasibility of a research topic for graduate school? Like if a topic is something that will be relevant for coming years, or is it just a hype topic? I think it's quite hard. I think it's okay to go in a research direction that not necessarily pan out. Not easy to answer a question. I think like reading quite a lot of literature, try to read a bit of every paper on or every different subfield. So pre-training, post-training, distributed, diffusion, etc. And reading a bit of everything to try to kind of see where the field is going, I think is quite important. So just be, I guess, will be well read and be willing to also switch topic if you believe the topic is not relevant anymore. I guess you probably should read, there is a manuscript written probably 50 years ago by Richard Hamming called You and Your Research, which is very relevant on how to do proper research. So it's Richard Hamming, You and Your Research. Anonymous, is there a relation between distributed learning and federated learning? Yes, federated learning is distributed learning. Is a way. Federated learning is basically doing a local training. So that's what I showed before. You could argue that there's many words basically in academia, like everyone name it differently. So you could argue that local SGD, federated learning, or DiLoCo is the same thing. It's local training. I think there's some differences. Federated learning was mostly focused, so there was a lot of emphasis on privacy, that each device must not link the data to the others. Also, federated learning do a lot of replica, so sometimes in the multiple thousand of replica, but then they don't care about flop efficiency, which was fine because at the time they were trying maybe for medical data or small data sets. If you want to train a big LLM, federated learning don't care about flop efficiency, but that's a problem. You need to care about flop efficiency. Federated learning also do a lot of like replica sampling, and they also care whether if the replica is actually hostile, so whether you can trust that replica or not. So it's similar and yet also different in some way. Can you comment on using distributed learning in vision model, more specifically in biomedical image domains? So if you use classical methods of distributed learning, yes, you can use distributed learning for vision model, for biomedical stuff. If you use stuff like DiLoCo, DiLoCo will work well on a transformer. I think it will work quite poorly on convolutional neural networks, but probably you still use transformer right now nowadays, even for computer vision. I don't know enough whether it will be very different for biomedical image domains. I cannot tell you for sure. I'm sure if you look in the federated learning literature, there's probably tons of paper about that because they care a lot of privacy. So you can probably look in that direction. Raphael Manlid, do you see any non-gradient model training that can compete? No. That's kind of the dream that everyone would like to train your model without gradients, maybe with Avian learning, other like neuroscience-inspired method. It's kind of a joke that every PhD student, I did the same. Like everyone, we want to find a way to maybe use non-gradient method and find other method like based on neuroscience that can train a model. So far, no one has managed to make something that is very competitive. If you could make it work, that would be great, but that's also very, very, very risky. Second question, how will Ultra Ethernet potentially affect which direction are the most optimal and affect how the optimal distribution mixture can look like? I'm not familiar with Ultra Ethernet, but even if you have better connection, that connection is always like limited to your inside your cluster. If you want to be across countries, for example, I don't think you will have a super great internet anyway. So you will, even if for planetary computation, you won't be able to just improve the hardware. You will have to change the methods. If you're inside the cluster, I think it's still, you still need to use a combination of all the classical distributed learning methods. So data parallel and tensor parallel, and maybe pipeline. Anshuman Singh. What is context parallelism in 4D parallelism in Picotron? I'm not exactly sure because I don't use that notation internally in Google. I think context parallelism is relatively similar to what I call sequence parallelism, where you split the across the sequence axis. So when you have like multiple tokens in a sentence, for example, you can actually split the computation across the sequence axis because when you do the feed-forward network in a transformer, the tokens are processed independently. So here you can split the computation across the sequence across multiple GPU. But then you need to gather back the token embeddings when you do the self-attention because they all communicate. But then you can do distributed methods such as the ring self-attention. Sashima Hossein. Very interesting to collaborate with you on your experiments. Can I reach out to you? So you can reach out to you. You can reach out to me. However, I cannot collaborate with external people. Yeah, so I cannot collaborate externally, but there is many people who are doing reproduction open source of DiLoCo. So I put a link, for example, for the NanoGPT and DiLoCo on internet. You can try to reach out to those authors or the authors of Prime Intellect and others and collaborate with them. Younes Kadar. Thank you for the talk. You're welcome. I was wondering, what are your thoughts about Hugging Face not supporting JAX anymore, especially with respect to the GDM JAX book you share? Is it worth trying to do multiple GPU training with JAX for people who are not at Google? So Hugging Face don't support JAX anymore because I think most of the open source community is using PyTorch, so that's fair reasoning from their side. However, JAX is still very well used. So Google used JAX, Anthropic used JAX, XAI used JAX. So I think many people use JAX. I think it's great, JAX. I love JAX. I think the book is still relevant because the book is like not, it talks a bit about JAX, but it's also like a lot of ideas that are very transposable to PyTorch. So I think it's still worth to read the books. And whether you should do GPU training with JAX or not, if you're not at Google, that's kind of depend on your setting. It's true that if you do PyTorch, it will be easier to have a collaboration because more people are familiar with PyTorch than JAX. Okay, I think that's all the question, or did I miss any?
No, that's all. Thank you so much, Arthur, for taking out so much time and answering all the questions.
Of course.
And for